Fantastic. Thank you, Victor. Thank you for giving me this venue to present. And although the talk today that I'm giving is coming from the aspect of efficient AI, as everybody knows here, AI is scaling in both the terms of memory and compute that it needs. The requirement is also growing significantly, and it's putting a lot of pressure on the technology that we have right now. So my work has been about accelerating AI from edge to scale. A lot of the work that I did during my PhD was one of the pioneering works to build full stack solutions for machine learning algorithms. And the goal there was that ML is an important enough application, it's going to grow, and it's going to need the necessary compute and memory bandwidth to to do the future innovations. However, we cannot rely on the general purpose compute stack because of the end of Dennard scaling and the limited scaling of Moore's law that we see right now. Instead, OpenAI has released that the models are growing at a rate of 3.5 times in about, sorry, 2 times in about 3.5 months. So the scale at which the model size is growing and the amount of compute they need is growing is significantly higher than what the current silicon can provide. So we really need to rethink this stack from top to bottom programming languages down to the hardware accelerator and how that hardware accelerator fits with the peripherals, which is memory, IO, networking. And that's kind of what my work is right now. Today, I'll talk about two separate works and then dive in from those insights how we should rethink about the next generation systems for AI. So my talk is about accelerating AI from edge to scale. One of the works is looking at the edge side of the problems, and the other work is looking at the scale side of the problem. So as we all know, when an application becomes important enough, plus at the same time, general purpose compute cannot provide us the benefits, specialization is there to meet the computational demands of these large models. It is Today, it's taken for granted that domain-specific accelerators, be it GPUs, TPUs, and any other accelerator, Microsoft Maya accelerator, is going to be specialized for these AI models. However, specialization comes with their own challenges because we need to rethink the entire system stack. We cannot just build a hardware accelerator and call it a day. Instead, we need to look at the algorithmic innovation. That's what is defining how large these models are becoming. And at the same time, we have data revolution. uh, I remember about a year ago, ChatGPT or GPT 3.5 was trained on about 530 gigabytes of uncompressed text data. So the sheer amount of information that these models are consuming is also really, really high. And to cater to these algorithmic innovations and data revolution, we need to rethink our infrastructure, architectures, and systems which deploy these large scale models. And at the base of building these architecture and systems, we have the substrate, the silicon. Where does the memory sit? How do we bring the memory closer to the compute? How do we provide sufficient compute throughput for these models? And how we don't hit the power wall. That's going to be one of the key challenges that I'll tackle as a professor, where we are going to look at challenges as to, let's say we have the compute to run these models, but what is happening right now is that the power requirement is growing substantially of training or even inferring these models. So how do we build co-design, hardware software co-design of the systems which tackle this power wall challenge? So in this space of domain specialized acceleration, I have done some work across the stack. One of the first works that I did during my PhD and even after that was building specialized full stack solutions from programming languages down to the hardware accelerator, stating that we need these specialized compilers, programming languages, we need specialized architectures for these models. And now we see these frameworks like PyTorch, TensorFlow, TVM, all of these are kind of standardized. The next aspect that I tackled was that memory is, or data movement is an important part of the whole problems, and often data is stored in management systems. So how do we integrate these hardware acceleration solutions closer to the database management systems? And finally, memory and IO. As the models become larger, we kind of want to distribute them. Distributed execution has become very, very important. So how do we think about efficient distributed execution by catering to the memory and the communication aspects of these large scale models? So in this particular talk, I'll focus a little bit on the newer works where we have an edge solution, which is uh, fluid, which aims to tackle the heterogeneity of edge devices for distributed AI, and the FAY work, which aims to tackle the challenge of doing distributed training at scale. So now the challenge in this first particular work that we look at is there's a lot of system heterogeneity that we have right now. One of the things that is important in AI is that we are trying to run it on all sorts of platforms. We want to run it on the data centers that we have. We want to run it on the mobile devices that we have. Google just recently released their Gemma models, which are very lightweight and can even run on an iPhone. So we have a lot of this heterogeneity. But even in a data center or even at the edge, if we think about it, there's a lot of system heterogeneity. And most commonly, when we talk about edge-based training for these AI models, it's federated learning. And we often observe that there's a vast heterogeneity in the training time. And what happens is that the devices which are slow, and often what will happen is that some devices will be faster, others will be slower, and there are a variety of reasons. The technology could be older. The things that are executing on those devices could be taking up all of the battery. The battery of the mobile device could be low. So there are a variety of reasons why there are certain devices which are significantly slower than the others, but they do dictate the overall execution time. So they kind of become the bottleneck of the system. So if we look at an example system, we in federated learning, we have a server which keeps the model, which keeps a global model, a uniform model, AI model, but the client train on their local data. We don't want to share. One of the unsaid rules in federated learning is that we don't want to share the data that we have on our phone to the server for privacy reasons. So every local device has to train on their own information. However, there are some straggler devices, and when we talk about model aggregation or synchronization, those straggler devices kind of dictate the overall latency of the execution. Now, what prior work has done is that it says that if we have some devices which are slower, let's just skip those devices. Although that has negative implications in the sense that if you skip slower devices, you're just skipping the insights and information that we can get from them. Instead, there were some of the other works called federated dropout, which aim to reduce the computation and communication load on those slower devices. And those computational load means that you reduce the model size. So you randomly drop out part of the model on these stragglers, or you do an ordered dropout where you say, oh, I'll just skip the first part of the model. So that has been the state of the art in this particular space. However, our recent work at NeurIP said that instead of just randomly dropping out things and doing executions which are not related to the relevance of the neurons, we might be losing something. So instead, we propose the idea of invariant neurons, where we state that neurons in a model train at different rates. And often what happens is that certain parts of the model get fully trained. So the blue darker neurons here are already fully trained even prior to looking at the entire training data. This is based on the properties what the model is capturing. So invariant neurons are layers or parts of the model which are already saturated and trained, and they kind of stop contributing to the global model training. The important aspect is that they are required for inferring, but they are not necessarily that important for the contribution towards training. And that's kind of what we observe in the in the in the in the invariant neurons when we try to see how they train over time. Now, what are the challenges when we want to create a system which knows about invariant neurons? So the goal of this work overall is that we perform the most relevant executions on the edge. We know that we have some information that we want to capture, but we only want to do the least amount of work with the most insight or the most advantage in training. But the problem is that there is a vast heterogeneity in the systems. The mobile devices go on, off. We might stop training because the battery is too low, and the background in iPhone or Android device might say that I don't need to train right now. The battery is low. I will keep the battery reserved for, let's say, more important tasks like phone calls and things like that. And then there are other scenarios where devices might, let's say, are disconnected from the Wi-Fi. So there's a lot of dynamism in this system. To tackle this challenge, based on invariant neurons, we created Fluid. It's an open source framework right now, super lightweight framework that aims to alleviate the performance overheads of these stragglers, which kind of are determining what the overall execution time it is. And this is done by excluding neurons that exhibit minimal variation during training, which is essentially the invariant neurons. So what our study finds is that the Fluid framework can dynamically adapt to the changes in the client during runtime and delivers performance speed ups, but at the same time, it also doesn't lose any accuracy. Instead, we can obtain higher accuracy compared to the baseline techniques such as random dropout and ordered dropout. So now looking at this particular framework, how do we create this framework? The first aspect is we want to measure the performance and identify what the stragglers are. And the server essentially does that. It starts with the assumption that we don't have any stragglers in the system, and it does the entire general federated learning process, but at the same time it's measuring the performance, and it does it for about 1 to 2% of the initial training time. So once it has identified the stragglers, the submodel then is created based on determining that how slow is the straggler. It is 30% slower than the faster devices. Is it 40%? Is it 50%? And based on this information, it decides what is the submodel. Should I reduce the model to be like 50% of the 50% of the model of the entire model size? So we create submodels for every device, and we train on these submodels only on the stragglers. So we executed this particular framework on real-world mobile devices, ranging in performance across the years. We also showed performance variation by throttling the performance by running more intensive tasks on these mobile devices. Across all the scenarios, what we saw is that we can achieve 25% overall training speed up. And now we have not changed the hardware at all, if we notice. And it's not like we're giving up on any, accuracy or anything like that. Instead, we actually get 1.4 points higher accuracy than the baseline techniques. And the overall training speed up also includes any overhead that this particular framework imposes. So the goal of this particular work has been to understand if, with the existing infrastructure that we have, can we mitigate these performance bottlenecks that we get, knowing that in machine learning model we have these patterns of saturation where model gets trained much faster than the remainder of the model, and so on. So that's kind of the insight in this particular work. And we showed the scalability of this work as well to thousands of clients, and we observed that we actually get accuracy improvements with a much lower variance compared to the prior work. So now that we looked at the challenges on the edge side, I will talk about one of the works which looks at which tries to tackle a similar challenge on the scale side of things for AI. But before I dive into that, does anybody have any questions?
Yes, Ramesh.
Yeah, thanks, Victor, and thank Divya for the presentation. Just a quick question: that performance improvement, where does it come from by eliminating the invariant neurons on the stragglers?
So the performance improvement comes.
I'm sorry, accuracy improvement, I meant.
Uh, so the reason why we get accuracy improvement is because in the other prior works, you are randomly dropping out neurons, which might actually be very important for the end-to-end training. Instead, in this work, we are only dropping out neurons which are already fully saturated.
Okay, so if you are not dropping out anything, then there will be, I mean, on that
We
baseline,
don't
there will
get
be no
any
accuracy
accuracy
improvement.
loss. I'm
Okay,
sorry.
got it.
Yeah, we don't
Thank
get any accuracy loss compared to the pure baseline in which we don't drop out anything.
thank you.
Thank you,
I actually
Ramesh.
have a question.
Rafik. Rafik is first, Kanat, if you
Okay.
don't mind.
Well,
I'm sorry.
Rafik.
Hi, thank you. Very interesting. How do you determine when to drop a neuron? You say fully saturated. How many runs does it have to go through in terms of weight rounds before you say, okay, it's saturated? And
So
what is the overhead of this monitoring?
That's a great question. So we run one epoch of training on the already existing training data to determine which neurons get saturated, and we recalibrate this after every epoch. It's not like we only do the fluid calibration once. We can do it even at a higher cadence than one epoch, but we currently do at a single epoch cadence. So after for the first for the first epoch, we do the baseline training to determine what are the stragglers, which neurons are invariant, and in the subsequent epochs, we again do this recalibration as well, and we use that information to drop out to determine both the stragglers and what the invariant dropout is. The user can tell us if they do want to calibrate either at a higher cadence at lower cadence as well. Regarding the overhead for the system configuration that I'm talking about, where we do calibration at and every epoch level, we get close to 13 to 14% overhead, but the 25% improved training time includes that overhead.
Hmm.
Thank you.
Thank you. Kanat.
Rafik asked the question that I had, both questions actually. I will ask a
Okay.
follow up question on that. So you are basically recalibrating for the saturation of the invariant neurons at the epoch boundaries, right?
Yes.
So if you do that, how is the locality affected, and what impact does it have on the training time? Because if you recalibrate and retrain and bring in a supposedly invariant neuron back into the fold for training, it
Yes.
affects all the connections, what you have in the local buffers, memory and whatnot. So what is the overhead for that typically?
Uh, could you elaborate on that question a little bit? If
So
I
yes, so you have taken out some neurons, let's say.
Yes,
Okay. So they are out of the training till the next epoch.
only
And
on the
they,
stragglers. Only on the stragglers.
I see. Okay. Okay. Got it.
Yes.
Okay. Thanks.
Yes.
That answers my question. So the
Fantastic. Yeah.
overhead would be minimal on
Yes.
caching and everything. Got it. Thanks.
So the invariant neurons are a concept at a global level, not at the local level. Just to, in case there was any confusion regarding that. So the server is the one which determines which are the invariant neurons by looking at the information that is available after that one epoch.
Thank you. Got it.
Fantastic. So now moving forward to the second work that I'm going to talk about, which is fail. So we think about accelerating distributed large model training, and I will talk about this particular problem space in the context of recommender models, but this is a problem that we are seeing in many other models as well these days, even in large language models. So often what happens in these larger models is that there is a conflation of what the compute intensity is and what the memory intensity is. This uh, uh, this difference in compute and memory intensity, where one is significantly higher than the other, is way more profound in recommender models. So recommender models have two parts, which is one is the embedding lookup. And even though large language models also have embedding lookups, recommender models have these embeddings of much larger size. These the most recent open source models have these embedding tables of a size of about terabytes, tens and 20 terabytes of data, and they capture all of the user and the item information. So these models are used to recommend things or determine click-through rate, for example, and they capture a lot of features from all of the potential users that are using, let's say, Amazon and the items on Amazon. So embedding is extremely memory intensive, but there is a deep neural network part of it, which is more compute intensive. So most often there are ways to execute these models, and one way is that we use a hybrid execution mode. So as I was saying, they face this major challenge that there's a big difference in the memory intensity of one part of the model, and there's a huge compute intensity of the deep learning model of recommendation systems. We don't see such a stark difference in compute and memory intensity for large language models, but it is actually becoming more and more profound that if we notice that the HBM size in GPUs and TPUs is constantly growing, but that doesn't mean that the compute engines are getting utilized significantly. So how do we think about this balance between memory intensity and the compute intensity? Coming back to recommender models, because these embeddings are of a significantly large size, let's say 10 terabytes, they are often either executed in a hybrid mode in which the main memory stores these embeddings and the GPUs is actually essentially executing the deep learning part. But in this case, there's a lot of communication between the CPU and GPU, which can take up to 22% of the total training time. There's another scenario where we can just execute everything on the GPU to mitigate this communication. But once we split a model in a GPU, there's an all-to-all communication where you have to gather the parameters, which incurs a significant overhead. And this is true even for newer large models like mixture of experts which are coming out, and that's one of the reasons why these models cannot scale beyond a certain point, because you essentially are growing the number of GPUs or you're growing the number of domain specific accelerators based on the memory requirement of this particular model. But what we observe is that there are fundamental properties which we are not exploiting. We're just assuming that the entire model is equivalent. However, we observe that there are certain inputs, certain training inputs that are extremely popular. This is not based on address. This is essentially based on content. A certain input will be constantly observed in a lot of training data. So for example, a particular item on Amazon is very popular. A particular movie on Netflix is extremely popular at certain point of time. But what that means is that these massive embedding tables also have a very strong access skew. So what we observe is that for 80% of the inputs or training inputs, only 1% of the embedding data is actually accessed and updated. So what we observe is how can we use this popularity in input data and access queue of the embedding tables to perform a significantly more efficient training, both in terms of performance and in terms of energy. But the challenge here is that we don't preemptively know. We are not an oracle. We don't know which inputs will be popular or not. So what we do is we observe that if we just look at 5% of the input data, the first 5% of the input data, if it is randomized, it will follow the same access pattern as the entire original data. So what we observe is on the y-axis here, we have number of accesses in log scale. X-axis has the actual embedding indices. What we observe is if original data has some access pattern, 5% of the data, that's the sample data, has the same access pattern. And the reason for that is that the embedding access skew is very, very high, that some embedding entries are accessed like 10,000 times more than the other embedding entries. And that can just be captured by the sample data as well. However, what happens is that when we train, we never train on single input. So even if one input is accessing all the popular embeddings, the most high access embeddings, instead, we train on a mini batch, which is probably 16,000 inputs, for example. All of those inputs need to only access these very hot or very popular entries. If that is the case, we can have a memory layout for a significantly efficient execution. So what we what we observe is that if we have random inputs in the training data, and even if 99% of the inputs were hot, which means they were only accessing the popular embeddings, there is a very low likelihood that the entire mini batch would consist of those inputs, only those inputs. So even if one input in that mini batch accesses the cold embeddings or the embeddings which are not that popular, then that becomes the challenge that we need to tackle. Because if you think about popularity, one very simple approach of doing a memory layout is that keep the popular or high access embeddings closer to the compute, which is the GPU HBM memory. Simple, right? If we store that in the GPU HBM memory, we can quickly access it, and we know those are the most highly accessed and trained part of the model. But if we do such a memory layout where the high access embeddings are stored in the GPU memory, whereas the low access are stored in the CPU or the main memory, the entire input needs to only access information on the GPUs, because otherwise the going back and forth to the CPU will become the bottleneck of the system. So to tackle this challenge, what we do is we shuffle inputs. We shuffle inputs such that a single mini batch only accesses hot embedding entries. So we segregate inputs also into popular and non-popular categories to create new input mini batches. And based on this insight, we create a significantly more efficient memory layout and end-to-end training pipeline for recommender models. What this pipeline does is, let's say we have some training data. Most of the inputs are popular, some inputs are non-popular, but they're scattered across. We use a small 5% training sample to determine which are popular, which are not popular, which embeddings are high access, which are not high access. Once we have classified these embeddings, we store the popular embeddings on the GPU, whereas we store the non-popular ones on the main memory. And we use this particular memory layout to do a significantly more efficient training execution. So we integrated this end-to-end pipeline with PyTorch and compared it with the existing open source works like deep learning based recommender models, time series based recommender models. And the important insight to keep in mind is that in addition to performance, we are able to reduce the data transfer in the system by 50%. And even though we incur some overhead, the end-to-end training is accelerated by about 60% and 80% compared to the deep learning based baselines. And we anticipate that, so this experiment was done across multiple nodes, but let's say we expand this idea to a very large cluster, the benefits will significantly increase because we'll reduce the overall data transfer in the system, which further reduces the energy of the energy consumption of the particular workload. So now keeping these two works in mind, even without changing the infrastructure, we have been able to get all of these performance and energy efficiency improvements. However, if we think about the next generation, as I said, there are two very distinct eras of usage in training AI models. In the past, the models were growing at somewhat what we had the Moore's law 2-year doubling period, but now it's a 3.4-month doubling period and it's growing and growing. The AlphaGo Zero model requires 300x more compute than what we needed a couple of years ago. So we have this extremely distinct compute usage area. So that's why we need to rethink our infrastructure, the hardware, and the substrate that we are running on. And then on top of that, we need to dive into algorithmic and statistical properties of both the model and the data to build significantly more efficient systems. So it's an era of hardware software co-design, as a lot of us will have heard again and again. Any questions?
Yeah, I have a
Well,
question.
Yes, please.
I actually probably missed when you said it. What is embedding?
So embedding is a structure. It's a structure which stores features. So in recommender models, we can't store, oh, the user is, let's say, me, Divya. Instead, it stores features that represent me. I'm in this particular demographic of age. I prefer to see these particular kind of movies, let's say on Netflix, or these particular items. So it kind of delineates items and members into features, underlying features which are common across different communities.
These are vectorized as some kind of a fingerprint for the attributes of the entity that is being trained for. Is that what it is?
Exactly. Yes.
Okay. Okay. Thank you.
So now thinking about the next generation, right, of the systems that we are building, what if we look forward to what are the bigger challenges? So as I said, data movement has been a key driver of LLM latency, energy requirement, and the low utilization on GPUs during training. So if we look at this particular graph, right, on these particular large language models, these are the GPUs. As we see that the capacity is almost fully utilized. It's not 100% utilized because this is the inherent inefficiencies of how we distribute a model, but capacity actually reaches a pretty good level of utilization. However, the compute is almost always close to 40% or less than 40% for these language models. And the reason is that we are unable to feed the compute engines at the rate that they need to be fed. That is one. And the other thing is, I was talking to some of my colleagues in AMD. The problem is that when we run these massively parallel, let's say, general matrix multiplication operations on GPUs, we can often hit a power wall. Even if we could run, if the compute by itself could run potentially more operators in parallel, we have reached the peak power. And that means that the frequency will be dropped. So there are these conflation of challenges, which is how can we increase the compute utilization, but not hit the power wall and keep the compute engine fed from the memory so that the bandwidth and IO becomes a problem. So how do we tackle these challenges that we are seeing? And that too, challenges which pull apart from each other. So the one of the ways to tackle this challenge is if we completely rethink how we are building these systems. How can we bring, let's say, memory close to compute, but do we necessarily need to bring that larger memory? Do we always need like 80 gigabytes of HBM? Can we have multiple layers of memory, which is significantly more energy efficient, but can keep the compute engines fed through more optimized, let's say, scheduling and operator execution? Can we exploit semantic similarity? Because a lot of these current applications have a lot of semantic similarity. So there are vectors which we need to look at, which are semantically similar. As we were just discussing, embeddings are essentially vectors. And more often than not, we want to look at more semantically similar vectors. And if we know this about these models, how can we use this to build a memory hierarchy which is more efficient for LLM or large, even multimodal execution? So keeping these aspects in mind, we need to build architectural and system level solutions. So in this one particular slide, I'm showing one example. How do we build like these data movement engines which sit between compute and memory so that they can keep the compute fed in the right manner in the scheduling approach that would bring the energy requirement down? But at the same time, they don't require us to just brute forcefully increase the memory size. On the right-hand side, we need to co-optimize the different aspects, which is accelerator design. So this is an accelerator design. How many cores should be there on an accelerator? How much memory do we need? What should the memory stack look like? How do we do device placement? How should we split a model across these multiple devices? And finally, what should the networking strategy look like? Because most often than not, we will be distributing these workloads across more than one accelerator. And we expect that such a co-optimization would give us at least 4x higher throughput, but a significantly higher perf per TDP if we do a co-optimization instead of piecewise optimization. Thank you very much. That's all I had for my presentation today, but I'm happy to take any questions.
Kanat, thank you, Divya. Kanat and
Divya,
Ramesh.
great presentation. I do have a question. Okay, so you are basically looking at the models for subclasses that are used often and keeping them in the HBM, right?
Yes.
So the 50% reduction, what is the number for large language models? Because uh, the large language models have some intrinsic properties that are very different from the ones you have for DNNs and CNNs. My second question also has to do with just a curiosity. If you train it, models are generated based on the training data.
Right.
If you take the training data and blindly do a correlationships and keep the highly correlated, data and use that to train the submodels
Right.
and identify them earlier. So how would that compare with what you are doing?
So I think there are two parts to this question. Let me handle the first part to the question, which is large language models. Yes, I do agree that they don't have that clear distinction between popularity and popular aspects and non-popular aspects. So let me differentiate between more highly accessed data versus popular data. So the popular one is which also gets updated more frequently. So we see a lot of variance in the update that this part of the particular model observes. For large language models, what we have observed is they also face the similar challenge of low compute utilization, but high memory utilization, even though it's not as profound as recommender models. One of the more recent works we employ, which is a little bit different than the FAY work, is how can we use PIM-based technology to do scheduling and multi-batch interleaving to increase this compute utilization without essentially increasing the memory utilization. That's one of the follow-on works that we are submitting. In LLMs, we have to do more fine-grained approach towards popularity. We can't just do such a large coarse-grained approach as we did in recommender models. Instead, in LLMs, we have to do more sub-batch interleaving at a much finer granularity where let's say a certain part of the attention model is a lot more heavily accessed than the others. And that requires more fine-grained scheduling than the coarse-grained scheduling that we saw in recommender models. Another example of this popularity and saturation is actually MOEs, a mixture of expert models, which are even larger than LLMs in terms of their sheer size. We observe for mixture of expert models, and this current work is in process, is that some experts are extremely more popular and some experts are very saturated. and we can have a better memory placement strategy of these experts so that we don't necessarily scale the number of devices based on just the memory requirement of the model. So the general insight across all of these models is that, is it necessary to scale the memory, or is it necessary to scale the devices based on the memory size of these models? Does that answer your first question?
Yeah, it does. Definitely.
So secondly, for the second question, when you mentioned about correlated input data, we don't want to change the training process at all. It's not like we train more on the popular data. If there is non-popular information, we are training that as well. In essentially, actually what we observe is it's very important to train on non-popular data, because let's say there is an embedding entry which is accessed 10 times. It's not at all popular. Very popular embedding entry is actually accessed 20,000 times and it's constantly updated. But training and updating that non-popular embedding is extremely important. We cannot skip it, because those few updates will lead to a much higher accuracy improvement. And I don't have that result here with me right now, but I'm happy to share it. So we don't change the training data. What we are doing is we are shuffling the input such that we can pipeline the non-popular and popular batches such that the latency of the non-popular batches is hidden behind the popular batches.
Got it. Thank you.
Thank you, Ramesh.
Yeah, thanks, Victor. Yeah, quick question. So, yeah, I see at the architecture level, you're focusing on different requirements, compute bound or memory bound, and therefore balancing compute, memory, and interconnect for that matter, because there's power burn there also. And I apologize, I miss your initial part of the presentation. So just asking whether when you say algorithmic level innovation we need, does it include things related to compute paradigm, uh, particularly for this level of heavy compute and power intensive applications? Because your focus here seems to be all on how to implement the DNNs and these LLMs better on hardware architecture, but how about alternative compute paradigms?
Uh, uh, could you give an example of the alternative compute paradigms?
Yeah, the examples are stochastic computing, neuromorphic computing, cognitive computing, which are, yeah.
No, that's actually a very great point. There's a complete separate line of work which is starting to look at how we can, why do we even need this much, this large model? So uh, let me be very, blunt in the sense that a lot of the algorithmic innovation has happened because we had the hardware for it right now. Right? Why are we running these massive game operations? It's because we had the necessary hardware, be it GPUs or TPUs, which are very adept at running these particular models. So transformer models are a perfect example of why they are popular, is because we have the hardware for it. So algorithmic innovation and hardware has kind of gone hand in hand and given each other feedback loop to grow in that particular positive in that particular direction. Although I do agree with you, we need to rethink, take a step back and rethink that, are we going completely in a different direction than what, let's say, how biology works, how neurons work. We need significantly lower energy to train on the same amount of information. We don't need as much training data to learn many things. And there is some components on the side of alternative model technologies like algorithmic innovations. There are these innovations on the existing hardware like sparsity and quantization. We try to move towards something which is not as compute intensive. And then there is completely other side of the compute substrate, which you're saying that we have stochastic hardware, we have neuromorphic hardware as well. So I have not necessarily worked on the last one that you are asking about, but what I can say is that there is certainly a huge merit in taking a step back and thinking about why are the models being created in a direction where they just, are increasing in a brute force manner, where they're doubling in a 3.5 month cadence. So for example, somewhere in between, when we think about models and sparsity, there are these a mixture of expert models, and these models are a lot more sparse, much bigger. They are closer to what we see in real world than large language models. But the problem there is that we don't have a better way of communicating, efficiently communicating across those devices. So my group is looking at, can we reduce the model size without, or squish the model size in a way where we don't always access the entire model for either training or inference, using a much higher coarse grained sparsity, so that we don't just increase the number of devices based on the memory.